All right, so guys, number 3, picking up where we left off. Again, if we want to stand a chance at successfully graphing these, I think that maybe a good step 1 is to remember what they're called. What are these called? Anybody recall? Those one things in the lead. Anybody can beat that?
I was in the lead. I think graphs.
You said numbers.
It's like the inequality system. System of equality. Inequality.
Still no.
Still no.
Still no. Anybody?
Wait, you guys know how to graph it?
Square root.
So the part that's inequalities, though, that again, that's our restrictions, our inequalities. So this is actually one function, but we have different pieces of the function. Piecewise function. There we go. I thought that hint may have done it for us. All right. Earlier in semester 1, as we prep for this semester 1 final. Yeah. All right, so guys. Here's how we want to go ahead and attack this. Obviously, this is very temporary, but again, I want us to just focus on one piece at a time. That's, again, what this piecewise function is all about, is we have one function, but it's broken into different pieces. When x is here, this is the piece that we focus on. When x is between this and this, then this is the piece. When x is bigger than that, then it's going to be this, or however many pieces it's broken into. This one, it was broken into 2 parts, into 2 pieces. Okay? So, our first piece that we're going to focus on, what if we just had f of x is equal to the square root of x minus 1 all plus 2? Would we feel like we know how to graph that? I think so, hope so. Again, I would encourage you to tie this back to our parent function, root x. That's where it's all going to begin. Again, if I were to put a 0 in place, the square root of 0 is 0. If I put a 1 in place, the square root of 1 is 1. If I put a 4 in place, the square root of 4 is 2. If I put a 9 in place, the square root of 9 is 3. This would be my parent function for the square root. Okay? Now, obviously this isn't my final graph. This is what we're going to adjust. What does the minus 1 under the radical represent? What are we going to do? Move to the right. How much? 1. What about this plus 2 on the outside? What does that tell us we're going to do? Up 2. Okay. So that means that each of these points, there's an infinite number of them, but there's 4 that we've really highlighted here, 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 and here. We're going to take each of these points and we're going to do exactly that. We're going to move right 1 up 2. Looks like I was able to do all of those together, except for this guy wanted to wait. Right 1 up 2. But this is what we're looking at. Okay, so these are my points. Make those a little bit larger. And that's what we're looking at. Okay? Everybody feeling confident and comfortable with what just happened. Okay, so we went from the parent function, the green dotted. We've moved right 1 up 2. All of our points moved right 1 up 2. At this point, are we okay with getting rid of this parent function? Sure hope so, because it's gone. Okay, now, what we also were claiming is that we have more to this function than just this part. Okay, there's actually going to be 2 pieces to this function. This is the first piece, though. Now, again, we have not addressed the restriction whatsoever. We'll do that at the end. But the second piece of this function, is just going to be linear. Now it's just going to say f of x. I'm going to write it as y equals, because I think we'll feel better about that. Y equals negative x minus 3. We recognize that slope-intercept form? And I can only hope that we haven't forgotten how to graph lines. What's my y-intercept going to be here, please? Negative 3. So I start y-axis at negative 3. What's my slope? Negative 1. So I go down 1 over 1, down 1 over 1. Continue this all the way off of our graph. We could even go up 1, back 1. Continue this way. This would be my line. All right. So far, probably just feels like we had to just graph 2 separate things on one graph, but no big deal, I hope, right? Okay, now just so you're aware, we're not finished, but this is how we would begin the problem. This is how I would highly encourage you, I should say it this way, to do the problem. Okay, now I just got through saying that we are building one function. The way this is drawn right now, is this one singular function? No, it fails what? Fails vertical line test. This would not be a function. we call this a piecewise function. So again, we know that we have some adjustments to make. So again, if I look back at the top line, the square root part, we're saying that this only exists, what we see in blue, that only exists when x is greater than 1. Okay? Well, where is x 1? There's where x is 1. We're saying that to the left of that, the blue does not exist. Pretty accurate. Okay? Yeah, we're okay with that. What if we would have had a whole bunch of blue stuff over here? We would have erased it. We would have crossed that stuff out, right? There is one little thing that we do have to adjust, though, because remember that restriction saying that this is where x is greater than 1, not saying greater than or equal to. So, Pitar, what were we saying we have to do? Yeah, right now, the way that it's drawn with a closed dot, that would imply that x equals 1 is included. It is not included. So we're going to have to leave this with an open dot. Okay? So now that our top line is complete, how do we feel about that? Not too bad. We get it. All right, so now we're going to jump down to the second portion, the linear portion, where we're saying that that line, the red stuff, that this only exists when x is less than or equal to 1. Okay. So this part over here, is this where x is less than or equal to negative 1? Yeah, so that's all there. That's part of it. Until we get to 1. This is where it stops. This is where it stops existing. So what do we do with anything that is beyond that? It's to the right or greater than 1. We erase it. That's not part of it. This is no longer part of our solution. It was part of our original graph, but our restriction is now going to look like this. This is a piecewise function. Now, is it possible to have more than 2 pieces? Sure. Again, I think that if we go all the way back to first quarter when we were doing this stuff, I think we went up to having 4 pieces. Okay? But again, knowing how this works, we're going to be perfectly fine. Okay, now is it a function? Yes, now it passes the vertical line test. There are no places that we have overlap any longer. Okay, now what about the domain? This is one spot that sometimes people struggle with, at least initially. What is our domain? Yeah, so if we're looking at the red line, we're coming from negative infinity and we're going to 1, which is included. If we're looking at the blue line, we're going from 1 not included all the way to infinity. But we're looking at this as one thing altogether. Is there anywhere that x is not defined? No. Again, please understand, this is not a vertical asymptote. We are defined, if x is exactly 1, yeah, we're still on the red line. But as soon as x goes beyond, we just jump up to the blue, and we go from there. So the domain is still going to be from negative infinity to infinity. It's still everything. Now what about the range? We go from low to high. What's my range? What's my lowest point, please? Negative 4 is included. What does it go up to? All the way up to infinity. All right, guys, how do we feel about the piecewise function? Carol, Ryan, you guys getting this too? I was going to say you're getting your mime skills are on point back there, but I think the point is to change before your hand comes through, because you're going like this. You're going like. All right, so back to this. I'm glad we're capturing all this on recording. All right, so guys, number 4. I would hope that you agree with me when I say that number 4 is by far the easiest question that we're going to cover. Okay, so this one does not require any sketching, graphing, anything like that. It's literally just describe the transformation. So if we are thinking back to the parent function, what is the transformation that's happening? What's taking place here? We're moving to the right 1, and we're moving up 2. That's it. What if, there is not, but what if there were a reflection, just like we had a couple slides back? Is it okay to just say reflection, or do we need more? We have to tell where we're reflecting over. So like we did, like I said back here, we said it's reflected over the x-axis. So again, please understand, for full credit, like that has to be there. Yes?
So, it reflects over the y.
If you had a negative in front of the x. Right.
Oh.
Correct.
I know.
Correct.
Thank you.
All right, so logarithms. This is the other one. I would say that just in going around spot checking both second and seventh period on the blue packet, can't remember now which twos, the last two problems or two of the last three problems, we're dealing with the piecewise functions. That seemed to be those seem to be the biggest ones that were throwing you off. But I know that some students were struggling with graphing the logs. All right, so when we are graphing log functions, I want, hopefully, for you to be able to make the connections where if a couple slides back, you were good with graphing the exponential, we should be good with graphing the logarithm. They are literally just inverses of one another. So it is a terrible, terrible option, but it's technically an option. But could we turn this into an exponential function? Graph it like an exponential function, draw on the line y equals x and reflect all the points over. Could we do it that way? Yeah, I would not encourage anyone to do it that way. I'm saying worst case scenario, you sit down, you start the test, and you're feeling great about graphing exponentials, and you just can't remember how to graph a log. That's an option. We could take a logarithm, change it to exponential, graph it, reflect it over the line, indicating inverse. We could do it that way. Okay? At least. Yeah. Minimum of two. Minimum of two. Minimum of two. All right, so when we look back to this, again, for the same reasons that the exponential might be a little weird, same story goes here with the logs. That if we try to tie this back to a parent function, it doesn't exactly have a parent function by definition. Because log base 3 of x, we'll use the same. Log base 5 of x, log base 10 of x, log base 250 of x, they're not going to be exactly the same. They're going to start exactly the same, but they're not going to be exactly the same. Their beginning, their initial stages, like I said, though, are going to be identical. Which point will all four of those hit? 1, 0. Each of those are going to hit that point. For the same reason that the exponential, remember, a logarithm is just a different way of writing an exponential function, right? So, for the same reason that whatever your base is, raised to the 0 equals 1, that's why we are here. It's just that the difference between exponential and logarithmic is that in an exponential, x is your exponent. In a logarithmic, if you switched it back, the y would have been your exponent. So again, we're still dealing with that idea, that concept that anything to the 0 is just 1. Okay? What about restrictions? Now, do we have the ability to plug in whatever we want for x? No, we don't. No, we don't. If we end up with 0 or a negative inside of those parentheses, you're not going to be able to do much with that. Okay, like that's going to lead to an error. So what we're saying is that we can't be 0, we can't be negative. Kind of sounds like we have a vertical asymptote right there, which is exactly what we have. All four of those are going to start with this exact same beginning. We have a vertical asymptote at the y-axis at x equals 0, and we hit the point 1, 0. It's finding the second point. That's where these are all going to start to differ. So remember, second point. We remember how to do it for an exponential. We want 1 comma the base. What do we suppose it's going to be here? Base, comma. So if we were doing log base 250 of x, where would that secondary point be? 250, comma 1. Okay? Or log base 10 would be 10, comma 1, or 5, comma 1. But the one that we're doing, we have log base 3 of x. Where's our second point going to be? 3, comma 1. Now, I don't know the reason. I can't say with any validity why this happens. But a number of students back in Chapter 3 and in previous years also have thought that maybe we should count right 3 up 1 from this first point. That is not true. It's from the origin. It's from the origin we count right 3 up 1. Okay? Now, this one we could fit the secondary point because, again, if I were to think about, well, 3 squared is going to be 9, we could fit it in this way, but this is going to be our parent function. Now, in terms of the parent function, what are we doing to this parent function? How are we adjusting or transforming this? We're going to move to the right 4. So everything moves to the right 4. I'm actually just going to start by moving everything with my vertical asymptote. We're now going to be at x equals 4. And then all of my points. This is going to move to the right 4. here.